What is the coldest and the hottest thing in the universe? Let's embark on the journey from the lowest possible temperatures to the reality-bending enormous numbers. A few of those strange curiosities may be closer to you than you think. We can't talk about the coldest and the hottest without understanding temperature. Imagine this. You pull up to a gas station at 2 AM. You see some shady guys under influence of unspecified substance. They look a bit unstable. Those are particles. And the stuff they are on is energy. When they get more of the energy, they start to tweak more and more. That is the temperature. On an atomic scale, all particles vibrate and bump into each other, provide more energy to them, and their kinetic energy increases, so temperature rises. There are many ways to measure it, through changes in electricity in thermocouples, through changes in pressure and volume of materials, for example in mercury thermometers, and most important, through a thermal electromagnetic radiation in pyrometers and infrared thermometers. Temperature can be determined by length of electromagnetic waves emitted by almost everything.
Oh, that's hot!
So this is how scientists can determine temperature of things that would vaporize you in a millisecond. There are three most commonly used units of temperature: Celsius and Fahrenheit, used mostly in non-scientific circumstances. Which one is better? It doesn't really matter in everyday life, and only depends on what you are used to. From scientific standpoint, kelvins are the best. This unit is directly tied to the energy and starts at 0 degrees Kelvin, which is also known as the coldest possible temperature, absolute zero. At this temperature, particles don't move. All things seem to be frozen in time. It equals to minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. This temperature doesn't exist in our universe. It is only theoretical. Scientists managed to come close to it, 100 picokelvins above absolute zero. A bit above it, we have the average temperature in space, 2.73 kelvins. But temperature close to stars and other celestial bodies can vary a lot. At around 55 kelvins, oxygen in air freezes, changing to a solid state at normal atmospheric pressure, so even air can be frozen. But those extreme temperatures are only attained in specialized labs. In our solar system, even the furthest planets are a bit warmer than that. Neptune, 8th planet, has a mean temperature of 72 kelvins. Uranus, 7th planet, 78 kelvins. Next, Saturn, 135 kelvins. 5th, Jupiter, 165 kelvins. 4th, Mars, 245 kelvins. Earth has mean temperature of 289 kelvins. Next, Venus, which is actually the hottest, sitting at 744 kelvins. And finally, first planet, Mercury, which is at 703 kelvins during a day, and very cold at night, with only 93 kelvins. But those were just mean values. Even on the Earth, temperature can be different in places. The lowest recorded temperature is 183.95 Kelvin, minus 89.2 Celsius, or minus 128.6 Fahrenheit, measured at Vostok, Antarctica. It is almost impossible to live there. Without special habitats and cold weather gear, you would get frostbites in mere minutes. Overall temperatures at the coldest continent are not that serve, and depending on the time of a year and how close to a warmer coastline you are, it could be quite manageable. Let's take a look at some temperatures that we deal with in our everyday life, to better see a huge difference between the coldest and the hottest on this scale. Since we can't go lower than absolute zero, it is only 273 kelvins from the point at which water turns from ice to a liquid, another 100 kelvins, and it turns into a steam. We usually operate in those 100 degrees. Average human body temperature is around 310 kelvins. 36.6 Celsius or 98.6 Fahrenheit. If we go a few degrees higher, at a high fever temperatures, 314 kelvins, 41 Celsius or 106 Fahrenheit, our bodies start to slowly break down. Average temperatures on Earth are close to our internal body temperatures, at 289 kelvins mean and 296 kelvins average room temperature. Even the hottest place on Earth, Death Valley, reached only 329.85 kelvins, 56.7 Celsius, or 134 Fahrenheit. Now, time for some hot things that we can find around us. Fire, for example, can vary from 573 kelvins butane flame to even 3573 kelvins oxyacetylene flame used in welding. Closer to us, wood burns at 1300 kelvins and charcoal can reach 1663 kelvins, and iron melting point sits at 1811 kelvin. Lava can reach 1473 kelvins, but in the Earth's core, magma under high pressure is around 5475 kelvins, and the hottest natural occurring temperature on the Earth is lightning. At the moment of strike, lightning channel can go as high as 28,000 kelvins, around 5 times more than the surface of the sun. This high temperature causes air to expand rapidly, producing sound, thunder. Even this doesn't come close to the next phenomena found in the vast universe. The sun's surface is only 5800 kelvins, but same as with the Earth, its core is much hotter. Extreme pressure, nuclear fusion, and the movement of hot plasma raise core temperature even up to 16 million kelvins. Pretty high, right? Yeah, but humans created a thing that surpasses it tenfold. I'm talking about thermonuclear explosion peak temperature, 350 million Kelvin. Of course, it is only at a small point, for a fraction of a second. Where do we find higher temperatures? The Sun is pretty hot, but on a stellar classification, it is only a G-type. Above it are F, A, B and O types, each one emitting a different color of light, with increasing temperatures. The hottest O-type stars appear to glow in a blue hue, and can reach surface temperatures above 30,000 Kelvin. They are of course magnitudes hotter at the core, but since we measure it through electromagnetic waves emitted from the surface, it is a big unknown how hot it is. We can estimate that before collapsing and exploding into supernova, it can reach even 3 billion kelvins. After that, neutron stars are formed, with surface temperatures of million kelvins at the beginning. So, is there anything hotter? Two neutron stars, smashed together, merging and reaching the highest temperatures in the universe, even up to 350 billion kelvins. So, is this the highest temperature naturally occurring? Yes, but to see the highest observed temperature, we have to go to a special place, the Earth, and more precisely, Large Hadron Collider in CERN. Here, scientists smash together particles in the largest collider on Earth, researching the most complicated physics topics known to a man. And in 2012, when looking for the Higgs boson, they've collided two protons accelerated to speed close to that of light. Estimated temperature during collision is 5.5 trillion kelvins, and this is the highest temperature in the universe, achieved by humans in our pursuit of knowledge. Wait a minute, if there is absolute zero, is there the theoretical highest temperature? There is, and it is called the Planck Temperature. Same as with absolute zero, it is obtained through electromagnetic waves. At the lowest temperature, wavelength reaches an infinite length. So on the other end, the maximum temperature would emit wavelengths reaching infinitely short length. At this point, as with other things named after Planck, our understanding of physics doesn't work anymore. We don't know what would happen with the matter when reaching this temperature. It is speculated that this is how hot the universe could be at the Big Bang, when all matter and energy were concentrated to a seemingly infinitely small point. And the theoretical number is equal to 1.42 times 10 to the power of 32. Trillion times higher than the record temperature. So the coldest, theoretically possible temperature is absolute zero, and the hottest is Planck temperature. And that's it. I hope that I managed to show you huge disparities in those extreme temperatures. If you enjoyed this video, subscribe and leave a like. You can comment what do you think about this topic, and remember to check out my other science-based videos. See you in the next one.